Now let's look at our second example here. How we can determine the stability of equilibria using derivative method. So the system we are looking at is the second one that we were talking about. Okay, so let's move down over here a little bit. So we have the system x prime is equal to let's go back a little bit. It's going to be negative x plus xy minus x squared, and y prime is equal to y minus xy. So this is the one. Now we need to take partial derivatives. So f of xy is equal to negative x plus xy minus x squared, and g of xy is equal to y minus xy. Okay. First of all, let's recover the equilibria we actually did it before. So f of xy equal to 0 implies x times minus 1 plus y minus x is equal to 0. And g of xy equal to 0 implies y and 1 minus x is equal to 0. So x dot is, or x derivative is equal to 0, we have 2. X is equal to 0 and y is equal to x plus 1. And y prime equal to 0, we have y is equal to 0 and x is equal to 1. So combine these two, we have 3 equilibrium. If x is equal to 0, then y must be equal to 0 over here, and then this is 1. And if x is equal to 1, then y is equal to 2. That's another one. And the other one over here is that when y is equal to 0, actually x can be negative 1 from the first one. So we have 3. Now what do? We now take the partial derivatives. Partial f, partial x, that's going to be negative 1 plus y and minus 2x. And partial f, partial y, that's going to be just x. And partial g, partial x, that's negative y. And partial g, partial y, that's 1 minus x. So we have the Jacobian matrix over here. We have negative 1 plus y minus 2x and x minus y and 1 minus x. Now we need to plug in the values of these equilibria and look at the matrix. So at this point, at 0, 0, the matrix becomes negative 1, 0, 0, and positive 1. So we have 2 eigenvalues. One is negative 1, and the second one is 1. Because of this positive eigenvalue, this is unstable. Because of this negative 1, one negative, one positive, this is unstable, and it is a saddle. Okay, and then let's look at a point when x is 1, y is 2. Then our matrix becomes the following. Y is 2, x is 1, so we have negative 1 over here, a 1 over here, and y is 2, so we have negative 2, x is 1, we have 0. So now we need to use the equation that lambda I minus a equal to 0 to find eigenvalue. This is lambda minus negative 1 becomes lambda plus 1, minus 1, 2, and lambda minus 0. So we find its determinant and then set to 0. So we have lambda, lambda plus 1, and then plus 2 is equal to 0. So we have lambda squared plus lambda plus 2 is equal to 0. We can use a formula to solve it. Lambda 1, 2 is negative b plus minus square root b squared minus 4ac, that's negative 8, divided by 2. So we see we have negative 1/2 plus minus I and square root of 7 over 2. And the real part of the lambda is equal to negative 1/2 is less than 0. Because of the complex root, and because we have negative real part, so 1, 2, this equilibrium is a stable spiral. It's a stable spiral. Now we have our last point to look at. It's just exactly the same. So now we have point x negative 1 and 0. Look at the same Jacobian matrix, plug in the values. X is negative 1 and y is 0, and this one over here is 2, and this one over here, x is negative 1, y is 0, so we're going to have 1 over here. And then we see lambda 1 is equal to 1, lambda 2 is equal to 2. Both of them are bigger than 0, and this is a repeller. This is repeller. Of course, repeller means unstable. Okay. That's all we want to discuss for 2D systems, how to determine the stability of an equilibria, and also how to draw the phase diagram using the locus method or the null line method.